take a look at how Excel can help us with this particular example. So we're going to look here at the charge, or rather the voltage across the capacitor. So this formula here describes how the voltage across the capacitor changes in time. That's what the T there's for, minus T, which I'll explain in a minute. Refers to time. Vs is the voltage supply. And what this part here, this 1 minus e to the minus t, is a ratio. Gives us a ratio between, in this case, between 0 and 1. If you multiply that by the voltage supply, that's the maximum voltage that this capacitor can get up to. Okay, so that's what that refers to. Now, E in this situation refers to Euler's number, the exponential, where E is 2.71828. So that's what we call the base. T is the time. So it's the power that you raise it to. And it causes an exponential increase as long as the time is above 1. If it's 1, it stays the same, obviously. Okay. So what happens here is it causes the change. So let's have a look at some examples. So exponential growth and decay are common terms, and this number here, 2.71828, is just a small version of a very long number, an infinitely long number actually. It's what they call an irrational number that goes on forever, never repeats itself, just like pi. So exponential growth, which we're all familiar with, is this. Let me just show the graph. So what I've got here is a plot showing how, as time goes by, the growth increases, keeps getting steeper and steeper. Never gets to be vertical, but it keeps getting closer. Incidentally, it crosses the 0 point of time at 1, which is logical if you think about it. It's got to start somewhere and it's got to start at 1, otherwise there's nothing to grow. So it starts from 1 and goes upwards. But that's also reflected in that anything to the power of 0 equals 1. So e to the power of 0 equals 1. So the times 0, so it equals 1. Okay, so that's your growth. That's what we see with things like bacteria, populations, things that in nature grow. Now, in theory, in the maths, this would keep on going up and up and keep on increasing. But of course, in reality, that can't happen because, take bacteria, for example, or the virus, it can't keep growing because it tends to kill its host, or its host reaches a maximum population if it doesn't kill them, it spreads. It can only affect the total population that exists, and that population has its own limits, like food supply and space, etc. So these are limit in the end, but in theory, mathematically speaking, it will keep on increasing. Now decay, as the name suggests, is the other way around. Excuse me. So this one starts at 1 and then goes down and decays. And what happens here is, as it decays, it keeps getting down towards 0 as you go on in time. Excuse me. So it keeps decaying in time, but never actually arrives there. It's what they call an asymptote, when it goes towards a value but never arrives. It keeps bending away at the last moment, should we say. So it never actually gets down to 0. So this is the decay. Now if we go back to our formula for our capacitor, what we've actually got there is the formula for decay. And we're going to take this away from 1. So if we multiplied out this bracket Vs, we'd actually have Vs minus Vs times this ratio. So what that would be doing mathematically is be defining how the curve is increasing towards the limit. So the rate of change is actually decaying, it's getting slower. So that'll affect the fact that we can never get higher than Vs. In fact, as we'll see in a minute, we can never actually get there because of one of the issues of this equation, this formula, this function. So let's have a look. Excuse me. Okay, so we've got here, we're going to do voltage growth against time. So let's do some times. So what I've done here, so a lesson in Excel, so I can put some times in. So 0, as long as these incrementations are in a linear manner, so we've got 0, 0.2, 0.4, 0.6, I can actually draw this down to any value I want to. So what I'm going to do is I've got it's going up in 0.2s. If I take that corner there, I can pull it down and you can see it incrementing. I'm going to take it all the way down to 5 for reasons I'll explain in a bit. Okay. And then I'm going to take a formula, our formula here, this formula. I'm going to use this one, but I'm going to treat VS as 1. So basically it's unity, it doesn't change anything. So that'll give me a formula that looks like this. So when you're doing a formula, the first thing to do is put an equal sign in. Okay, I'm just going to make this a bit bigger so you can see this better. Whoop. Let's just go back a step. There we go. Okay, so I'm going to put equals. It tells Excel that I'm putting a formula in. Then I'm just going to go for the treating it as our VS value as being 1 volt. So I don't need to put it in. I'm just, for this stage, I'm just going to put 1 minus, and then for Euler's number, the exponential growth, in Excel we use EXP, then we have open bracket, and then this stuff that was to the power goes in this bracket. So this is going to be minus T, but instead of putting T in every time, I select this cell here, which is A1, not A2. You can see it's entered it automatically for me. And then if I just hit enter, it'll actually complete the formula. I don't understand the error message. It's telling me it's corrected it to the same. I'll accept its change anyway. You can see that it's just the same. 1 minus exponential minus A2. Okay, now the beauty of Excel is I can now take this formula, select it on the corner and drag it down. And what that's done, if I select the second one, I don't know if you can see this clearly, but it says 1 minus EXP in brackets minus A3. So it's automatically put that data in there, that time. And it's done the same. Next one's A4, A5, A6, so on. So it's incremented it for me. So I've now got the final answers. You'll notice it starts at 0 and goes up to 0.99326. More on that to come. Right, I'm now going to insert a graph. So I'll select the data I want to make the graph with. You don't have to select the title at the top, but I'm going to do, because it'll automatically put this title into my graph for me. Okay, my favourite insert and my favourite graph for this kind of thing is the scatter one, the one that where it draws the lines in. So that one there. Right, let's make this a bit smaller. Bring this over the bit, make it as big as I can. Okay, I'm just going to tidy these axes up a little bit because it's got wasted space here. It's going higher than further to the right than is useful. So if I click on the axis here, I get this option up. I'm going to make my increments 0.5. So that you notice it goes 0, 1, 2, 3. I'm going to make it go up in halves, and I'm going to make this go to 5.5. Yeah, I'll take that for now. From 0 to 5.5. And going the other way, I can't do it on this one. So I'll accept that. Okay, and this one, I'll probably leave it as it is, but that's the method. Now let's do it just to show. So I double click on there, and I get the same function. So I'll make this go to, let's have to change this to 1.1. And then change this to 1.1. That's probably a little bit better, and I'll accept that. Okay. So that's the plot of what's happening to my voltage across this capacitor. So it starts at 0 in 0 time. Turn on the switch, it goes up, up, up. As you see, it goes towards the max value, which in this case is 1 volt. and that's the best it can do. It's head towards 1. As I've said earlier, it never actually gets there, which is shown in our data. At 5 seconds, it's got to 0.99326. So that's why I picked 5, incidentally, because going back to our formula, this one, this t here is the time, obviously. If you divide, just taking that as it is, a standard 1 second, part of the formula says that in 1 second it will always get to 63% of the charge, or 63% of the growth. So that's what we've got there, and you can see that on the diagram. 5 times that, 5 seconds will get you nearly to the maximum. Remember what I said, it never actually gets to the maximum, it keeps getting closer and closer, but never really getting there. But for our capacitor, it's near enough, so we treat it as 5. So what it would be in this formula, the time constant, as we call it, would be t divided by 1. And that defines the time constant. So say, for example, the time constant was 2, it is divided by 2, it would be 5 times that, so it would be 10 seconds to get to this fully charged state. Okay, so let's have a look at this. Let's say, for example, instead of, let's take it more like a real capacitor. So let's say, for example, that this is, let's multiply this. So I don't know if you can see up there, but I've put in brackets, I'm in the formula bar, brackets on it, and then outside the bracket I'm going to times it by, let's say, 12 volts for 12 volts. One side, so 12, and then we use the asterisk as a multiplier. Still 0, and then if I drag that down, the formula is going to change. So now we see the maximum we can get towards is 12 volts. Right, let's get rid of this graph because it's a bit messed up now, and do another one. So select my data, insert, scatter graph, the one with the lines on, that one. Okay, and you can see now it's going towards 12. I can obviously tidy that up. The next thing I can do that may be of use is, I said 12. Let's say, for argument's sake, that I don't use 12. I'm just going to get rid of this graph again, because I'm going to do another one. If it ever won't delete, come out of it, go back into it. Whoops. Yeah. Just got to get the right bit selected. Okay. Instead of putting 12 in, let's say we've got here 12. So V equals 12. So I put my voltage in this. In fact, let's put it over here. I'm putting this voltage is, and then it's 12. I could put a box around all that to make it distinct. Voltage is 12. So I can enter into there any voltage I want. So going back to my formula, instead of putting 12 in there manually, I can now put in that cell. Enter. So now if I drag that down, again, Excel will have incremented it for me. Something's gone wrong. Let's have a look at the formula. Okay, and now I know what I've done wrong. What's happening here is this one is incrementing automatically, which is a fantastic function in Excel. This time we don't want it to do it though. If you look at the next one, it'll say 2, 3, so it's going 2, 3, 4, and I need it to stay to be E1. So simple solution. Put the $sign in front of the number you don't want to change, or the value. So in front of the $sign. Enter. Okay, now drag that down. Bingo. There we go. So you can see it starts at 0 and goes up to 11. Excuse me again. So all I've got to do now, as my voltage supply changes, is just change this value. So if I put 24 in, for example, all my values change and I head towards my 24 volts. And plot it just the same. So that's the technique. So here I've got a formula now where I can just plot, just change this, and I get different values. In fact, let me show you just to finish. Insert, graph, scatter. Okay, make that a bit bigger. Okay, so I'm happy with that. Let's see what happens when I change the value. Let's go back to 12. Graph changes automatically. Now, tell me that's not clever. 240 volts. That's clever. Impresses me anyway. Okay, thank you for listening.